Thank you a lot for the introduction, for the invitation, and for being here in spite of the thunderstorm. So you decided to take your time and be here. So I hope I will present to you something that results interesting to you. I guess you work in different fields. So as Professor Shand mentioned. So the presentation will start with something about cultural heritage, which I guess is not everybody's field of expertise, but then I'll present to something about cementitious materials, which maybe is more interesting to you. The core idea is that materials and techniques that we use in cultural heritage conservation can be transferred also to the field of cementitious materials. Okay, so here you see a summary of what was just said about, let's say, who am I, why am I here presenting. So I think might be interesting is that I spent some years abroad in the United States and in Göttingen in Germany, working with experts in different fields. So starting from chemistry and material science to geology, because again, my core business is in conservation of cultural heritage. And as you can see, it's been a few years now since I started working on this field. Now I'm settled down in Bologna. I'm an associate professor, and since a few years, I'm also the coordinator of the PhD program in our department, which perhaps might be interesting to you in case you would like to spend some visiting periods at our university. Our university, meaning the University of Bologna, is here in northern Italy. It was founded in 1088, quite an old lady. So we claim to be the oldest university in the Western world, which is still running as such. As you can see here, Bologna is a nice, I would say, medieval city with a lot of historical buildings. This is our main library. I put a picture because yesterday we were discussing about libraries being like the ID of a university, of a studying environment. So I think it's interesting. Of course, we are also active in research in many different fields, from art and humanities to science to medical school and so on. The department that I work within is called the Department of Civil, Chemical, Environmental, and Materials Engineering. So we cover a broad spectrum of different topics and areas. You can see here an overview of the research domains here, particularly regarding material science and technology. So besides other fields that maybe are not interesting to you, like biomedical applications or polymers for different applications and so on. Regarding the built environment, we work both on materials for cultural heritage, what I work on, but also techniques like FRP. We heard yesterday a presentation on fiber-reinforced cementitious matrices for conservation of both masonry structures and concrete structures. At the same time, I myself and especially some colleagues work on corrosion of metal alloys, so especially steel, but also historical bronzes and so on. And we also work on developing new sustainable cements and alkali activated materials, also for storage of CO2, use of wastes and so on, which, as far as I know, are topics that are also, let's say, covered by the research that is going on here. So this is the plan of what I would like to present to you today. So I will first start with some, let's say, an overview of what we have been doing in the field of cultural heritage, so for preservation of stones and mortars. And then I will present you some studies, some results about how this can be transferred to the field of cementitious materials, including both the historical cementitious mortars and concrete and the new ones that can be developed nowadays. Okay, so first of all, maybe you are already familiar because let's say also here you have a wonderful cultural heritage made of many different types of materials. In the specific case of stones, there are many different processes by which stone deteriorates. Some are common also to concrete and cementitious mortars, so the effect of salts The problem due to frost, which maybe is not an issue here in Hong Kong, but for instance, I know in northern China, they have many issues of frost as well. Then there are problems linked to, for instance, microorganisms that develop on the surface of stone. The same happens also in the case of cement and other issues. So what material science and engineering can do for stone conservation is mostly acting on two aspects. So one is providing like a barrier on the surface of the stone substrate to prevent its dissolution in rain, especially in acid rain, or in a day like today with a huge thunderstorm. I guess there also some mechanical erosion of the stone surface takes place. The other, let's say, main activity that material science can do for stone is providing some consolidating action. What I mean in this case is that the idea is applying a product here in green, which is able to penetrate in depth in the material, inside the cracks and in the pores of the stone, and then through some chemical reaction, harden and bond the pieces together. So to increase the cohesion and the mechanical properties of the substrate. Okay, so here is like a short overview of these phosphate treatments, which were in the titles of what we have been developing in the last few years for these abilities. So phosphate treatments, so the idea behind this technology, let's say, is starting with a certain type of substrate. Here is a marble column, but it could be a different type of stone, a different type of architectural element. We treat this with an aqueous solution of a phosphate salt. So you will see this acronym here, the ammonium hydrogen phosphate. Here you can see the formula. So the idea is I buy salt, so white crystals, I dissolve them in water, okay, nothing, no organic solvent, anything strange. So I obtain a solution, something transparent with a viscosity similar to that of water, and then I apply it onto the stone by spraying, brushing, by applying a poultice and so on. And then in a matter of a few hours, one day, on average, we have a chemical reaction between the calcium ions from the substrate, the phosphate ions that we provide, and we form a new calcium phosphate minerals. The mineral that we would like, we aim to form is called hydroxyapatite, HAP. You see here the formula. It might seem strange, but like this room is full of hydroxyapatite because this is the mineral constituent of our bones and teeth, okay? So bones, for instance, they are made of an organic part made of collagen, within which there are crystals of this same mineral here, okay? So the core idea is using the substrate, provide phosphate ions, so has to have a reaction and form phosphate, calcium phosphate minerals. What can we do with this? So again, the first function that we studied was developing a protective layer, so a barrier to reduce the solubility of the substrate. Here in this graph, you can see like some easy tests that people do in the lab to check whether this barrier is providing protection to the substrate. So the idea is this is a small piece of marble. I put it in a solution with a slightly acidic pH to simulate rain. And then I measure the pH change over time. Why does pH change? Because this rain or acid rain is corroding the marble. So here, for the untreated marble, you see this progressive increase in pH over time. My goal is to reduce, ideally, to have a flat curve, because it means that my protective layer is acting as a barrier, preventing the solution of the stone. So here you see there is like a decrease in the curve. So for instance, the same level of pH is reached after a time that is twice as much. So I can think I have extended the lifetime of my model. However, this curve is not flat yet. Why? We performed some FIB observation of these protective layers, and what we found was that the barrier layer is quite porous. So because of that, it cannot provide a very effective barrier, because like rain, acidic rain is able to pass through the porosity and corrode the substrate. So by performing some, let's say, further research, we were able to densify these protective coatings. As you can see here, we found that by adding a little alcohol to the solution, it's possible to obtain a much denser coating, which is able to provide a much higher protective action, because in this case, rain cannot reach the substrate anymore. To further improve this protective action, we also investigated the possibility of forming the hydroxyapatite coatings through electrodeposition. So here the idea is something that was inspired by the biomedical field. I have some slides later in the presentation. So the idea is when one, for any reason, breaks a bone, usually or sometimes you need to have a metallic implant in your body so that the bone can grow again. For doing so, this metallic implant is usually made of titanium. This titanium is covered with hydroxyapatite, because as I told you, this is the constituent of the bone, so that the cells in our body recognize this metallic implant as something friendly and are able to grow. The new bone is able to grow on the implant. So taking inspiration from this, we tried one of the techniques that are used in the biomedical field to deposit hydroxyapatite over metal. So electrodeposition means electrode that by providing an electric field, it's possible to accelerate the formation of these coatings. And indeed, if we watch here, what was formed over marble for the same time without electrodeposition and with electrodeposition performed in certain conditions, as you can see, it's possible to accelerate the process of formation of these coatings to obtain a more continuous coating in a shorter time. A further different method to form protective coatings on the surface of substrates, in this case actually it's a cementitious substrate, is using microorganisms that form the same mineral, hydroxyapatite. So in this case, the idea is using some specific type of bacteria, providing them with some nutrient, and then the bacteria, through their metabolism, they create an alkaline environment, so to have precipitation of this surface layer of hydroxyapatite. So regarding, let's say, this first action, protective action, again, the idea is forming a surface layer over marble, but in principle can also be cement and so on, through different methods, a chemical route, electrochemical strategy rather than a biogenic one, in all cases to form this kind of surface layer to protect the substrate. Once we found out that we were able to produce these protective coatings, we thought of functionalizing them through some, let's say, nanoparticles or different, let's say, strategies to provide some additional action. For instance, self-cleaning or antimicrobial action. Self-cleaning means, maybe you are already familiar with this, the ability of a surface to degrade stains or soiling that forms, for instance, because of the deposition of pollutants onto the surface and so on. This can already be achieved by using nanotitania. Nanotitania is a photocatalytic material. It means it's activated by photons, so by light. So through UV irradiation with UV light, that's why I put violet here, these nanoparticles are able to activate some, let's say, mechanism through which they are able to degrade soil, pollutants, actually to also kill bacteria and so on. This is already known, it's already done since a long time, but the problem is when people apply these nanoparticles, for instance, as dispersions in water directly onto a wall like this one, okay, you obtain this photocatalytic activity, this self-cleaning ability, but the problem is when it rains, especially like today, these nanoparticles are washed away by rain because they are not chemically bonded to the substance. So what we thought was, okay, we saw that we are able to create protective layers on the surface. Let's try to use them to immobilize the nanotitanium nanoparticle onto the surface. So you see here, the idea was forming a protective layer, embedding the nanoparticles so as to obtain a durable, long-lasting self-cleaning ability. What we found was indeed that these coatings have a self-cleaning ability. You see here the idea. So usually these tests are done by having a substrate, in this case it was marble. We put a stain of methylene blue, a certain, let's say, chemical that forms a blue stain here. And then when the surface is functionalized to be self-cleaning, after exposure to UV light, the stain is fades away. Okay, so you obtain this kind of self-cleaning ability. The variation in color in doing this is a measure of the self-cleaning ability. So in these graphs here, you see that like the untreated stone has basically no self-cleaning ability. If you use the titanium alone, it has the highest self-cleaning ability. When you combine it with hydroxyapatite, you obtain some good ability. As I mentioned, the real problem is what happens once the surface is exposed to rain. So we did it in the lab, some accelerated aging. What we found was that titanium alone loses most of its ability because, again, the nanoparticles are leached away. If you combine the nanoparticles with the hydroxyapatite coatings, you see here, you finally have a residual self-cleaning ability that is much higher, so you have a very reduced loss of efficacy because of exposure to rain. So you are able to provide the surface with a long-lasting self-cleaning ability. More or less, let's say, in a similar way, recently we also received funding from the Italian government to provide these coatings with let's say, some antimicrobial agents. So in this case, we formed in situ some nanoparticles that have antibacterial ability. So what we found was that we started with model bacterial strains, so strains that are used in the biomedical field, Escherichia coli and Staphylococcus aureus. Later, we replicated with also environmental strains, so bacteria that are present on architectural surfaces. What we found was that for different types of substrate, as you can see here, differing in terms of composition and microstructure. In the untreated reference, we placed a certain amount of bacteria, they stay there. When the surface of the marble or limestone was functionalized in different ways, following like this idea here, you see nothing, but this is a good sign. It means that all the bacteria were killed. So after a certain time, the surface was totally antimicrobial, antibacterial, okay? So no bacteria were present on the surface. Same for the other cases. Also in this case, we tested the resistance of this antimicrobial ability to accelerated aging by rain, and we found good results, meaning this activity was maintained also after accelerated aging. Okay, let's reach the final ability function that we investigated for this in the case of stones and mortars. So the consolidating ability. So here for a new material, a new technology to be a good Consolidants, there are many requirements that need to be satisfied. First of all, in terms of effectiveness, I'm an engineer, maybe you are all engineers, so to me, there's no point in applying any treatment if it's not effective, okay? It sounds trivial, but it's not. So to be effective, it means that the new material should be able to penetrate in depth, because we don't want something that limits on the surface like for a few microns. We need something that is able to provide action also in that. It needs to improve the mechanical properties, okay, megapascal. But in doing this, it must be compatible. What do we mean? For instance, there shouldn't be any color change. If I have a white marble, I don't want it to become yellow or gray. But at the same time, also changes in the pore system, in the water transport properties, water vapor properties, and so on should be, let's say, controlled. All of this needs to last over time. We don't want something, the effect of which is lost in 1 year, okay? We want a long-lasting effect. And then in principle, it should be possible to treat again the monument in the future. We don't want to apply today something that cannot be, so that makes it impossible to treat again the monument in the future, okay? So there are some additional constraints. On top of that, as you know, nowadays we are facing many environmental challenges. Climate change is a problem. So also the environmental sustainability of these techniques need to be assessed, and I will present you some results about this. So going quickly through these results. Penetration depth. Again, I remind you, the idea is applying a solution, a liquid solution that penetrates in depth. Some years ago, we performed a comparative study where we compared the different application methods like brushing or a poultice applied onto the material. And then in this case, by neutron radiography, we were able to see the penetration of the consolidant in depth in the limestone in this case. So the black part indicates the presence of the hydroxyapatite. So the deeper the penetration, the better. This was also confirmed in terms of mechanical properties, for instance, in terms of resistance to abrasion. So we tested how well the material was able to resist an accelerated abrasion test on the surface, and then by cutting some slices from the surface, also at increasing depth down to about 7.5 millimeters from the surface, and we found that some mechanical improvement was present. And something good is that like the change in properties with depth is gradual, okay? There's not like a surface crust and nothing below. There is a continuous, a progressive change in properties with depth. Moreover, what we tested was many different mechanical properties. I think the most important one is tensile strength. I guess you know that also, similar to the case of concrete, you know that in the case of concrete, compressive strength is much higher than tensile strength, okay? Because it's a porous material, non-homogeneous, and so on. More or less the same applies to stone. The compressive strength of stone is usually great. The tensile strength is usually low. But so why were we interested in the tensile strength? Because problems due to salt crystallization, ice crystallization, and so on arise because of the low tensile strength of the stone. When we have a crystal of salt, for instance, or ice growing in the pore of the material, the crystal is growing, is pushing against the pore walls. So from the material point of view, it's like if I'm doing a kind of tensile test in this direction, okay? So I'm able to improve the resistance of the material to salt crystallization and so on if I'm able to increase its tensile strength. So we performed the test on cylindrical specimens of stone by the so-called Brazilian test. So you apply a compressive load in this direction, which results in an horizontal tensile strength. And as you can see here, so we started with a certain type of stone. we performed some artificial aging to induce microcracks that then we wanted to see. And then after treatment with DAP, we obtained an increase in tensile strength. So in this case, it was like a positive result. We also tested mechanical improvement in the case of lime mortars, which are used, in Europe, but also here. Recently, I've seen some very beautiful examples, for instance, also of wall paintings that are usually applied onto over a substrate and so on. So here, what we did was the so-called Scotch tape test, so a peeling off test, so to measure how much material is lost when you attach an adhesive and then you remove it. And again, the idea is by DAP, we are able to reduce the material loss significantly compared to the untreated reference or also some alternative commercial products. So also in terms of material loss by peeling tests, we found some good results. As I mentioned, it's important not to change the color of the substrate. This was the case. Here, for instance, you can see a comparison between the DAP treatment that we developed and the most commonly used alternative commercial. I think in this case, it's possible to see also on the screen that the marble becomes gray, which is something that, of course, you don't want in your monument. Recently, we also tested what happens if we apply this treatment, not only on stone with an homogeneous color, but also on wall paintings. Last week, I was in Xinjiang, in northern China, where I visited with some colleagues some mural paintings in some grottos, Kizil grottos. I don't know if you have ever been there as well. The point is, in that case, like in many others, we have like a thin layer of binder containing pigments of different nature. So in this case, the goal is to increase the adhesion between the paintings, the painted layer, and the underlying layers, but of course without changing the color and so on. So by this method, as you can find here, we found some good increase in mechanical properties. Again, here you can see this kind of peeling test. And in almost all the cases, the color change was acceptable. Usually, a color change up to a certain threshold, 5, is considered acceptable. So you have your monument, you apply your conservation treatment. If the color changes a little bit, up to 5 of this certain parameter is considered acceptable. Too much, a higher color change like this one wouldn't be acceptable because the material is becoming too whitish compared to the original color. In addition to laboratory mock-ups, we also performed a study on real frescoes coming from some monuments in Italy. And in general, we found good results on samples with different colors. Only in a few cases, the color change was actually not acceptable. So you see here, in this specific case, the initial sample had a very bright yellow color, which becomes, let's say, darker and not so pleasant after treatment. So in that case, it wouldn't be acceptable to use this kind of treatment. Chromatic compatibility is not the only requirement. We also need to check what happens in terms of porosity. We are introducing something into the pores, so for sure there will be some reduction in open porosity, some shift alteration in the pore size distribution, as we assessed here by mercury intrusion porosimetry, but overall the changes are low, so they are acceptable. As a result of the changes in the pore system, also the ability of the stone to exchange water and water vapor with the environment change to a certain extent. However, you see here the amount of water that penetrates into a certain sample as a function of time. In the case of an untreated stone, treated with DAP, it's almost the same, so it's fine. Here you see a totally different curve for the most common commercial alternative, which is called ethyl silicate. I don't know if you have ever heard of this, it's used also in the case of concrete. The, let's say, particularity about this treatment here is that it makes the surface hydrophobic for a certain time. One may think, oh, this is good. I have a hydrophobic surface. If it rains, rain is not able to penetrate. This is true, but coming to durability, what happens if, for instance, this is a sample that we treated in the lab? You apply the consolidants, this ethyl silicate on the surface here, which becomes hydrophobic. The problem is if you have a source of water from behind, for instance, because of rising damp from the ground, which is a quite common phenomenon, at least in Europe, but I guess also here. So here you see what happened to this specific type of sample where the surface was treated, so it became hydrophobic. We sealed the lateral surface and then we let water penetrate from above. After a few cycles, there was a sudden detachment of the consolidated part, which of course is something that you don't want in your model. By using this alternative treatment that we propose based on phosphates, we have formation of salts on the surface, which is not, let's say, beautiful, but at least we are not damaging the monument, because in this case, the stone remains hydrophilic all the time, so we don't have this kind of problem. Also, in the case of freeze and so cycles, you see there that in the end, the final goal, the final result is that we obtain better results compared to alternative commercial treatments. Okay, final requirement that needs to be satisfied for, let's say, any new consolidating product is also the environmental sustainability. Recently, we performed a comparison between our new technology based on DAP compared to the most common commercial alternatives. Something that maybe it's already common in other fields, but not much in the field of monument conservation, is what to compare to make a fair comparison. Because one may think, okay, I compare 1 liter of this, 1 liter of this, 1 liter of this, but 1 liter of each product doesn't provide the same action, the same function. So what we did was to, so we decided to use as parameter to evaluate environmental sustainability, the so-called global warming potential. I don't know if you are familiar with this. So the idea is quantifying the amount of CO2 that is linked to the production of the raw materials, the synthesis of the consolidants, transportation, application, and so on. Then again, to perform a fair comparison, we treated samples of marble, limestone, mortar, and so on, and we managed to evaluate the mechanical consolidation, mechanical effectiveness, so in terms of megapascals. So the idea is to compare products that are able to provide the same mechanical improvement. So we obtained some graphs like this one, which I think are quite interesting, where we plotted the increasing compressive strength. So we start from a certain megapascal of compressive strength and then we increase it as a function of the global warming indicator, so amount of CO2. So the idea is, for instance, if you want your stone is very deteriorated, so you need a 35% increase in mechanical properties, so a strong action. Okay, DAP is able to provide this mechanical improvement with a certain CO2 emission. The only other, so this consolidant here wasn't very effective, same for this one. The only other consolidant that was able to provide such high consolidating effectiveness was ethyl silicate. However, in this case, the amount of CO2 that is produced is basically twice as much compared to the phosphate treatment, the DAP treatment. Why? We see it here. The idea is called contribution analysis. So the idea is to see what part of the process contributes the most to the emission of CO2. In the case of the phosphate treatment, the DAP treatment, the solvent is water. So the amount of CO2 that is produced is quite low. In all the other cases, organic solvents are used isopropanol, white spirit, acetone, which contribute to increase the global warming potential. So the take-home message is we can provide the same or maybe even higher mechanical improvement with a lower CO2, which is a good news, let's say. Okay, I only reported one example of application to a real case study, which is this relatively beautiful sculpture in Versailles Palace in France, the Royal Palace. It's quite famous. I don't know if you've ever seen it, ever been there. So what we found, of course, we couldn't perform any compressive strands or tensile strands on a sculpture that is a few centuries old, so we could only perform non-destructive tests like ultrasounds or measurement of color change and so on. What we found was that after 3 years of exposure in the field, there was still some benefit that was initially present, also in the case of some samples that we exposed nearby. As you can see, there was some progressive decrease in mechanical properties over time, but still the treatment was able to provide some benefit. Okay, we have reached the end of the first part. The second one about cement will be shorter. If you have any questions so far, you can ask them now, otherwise later. Okay, so taking inspiration from the good results we found on stone, the idea was, okay, let's try to transfer all of this to cement. So the first step was considering like cementitious mortars with or without also steel bars, you can see here, that were constructed like 1 century ago or so on. In general, the idea is also in the case of cement or natural hydraulic lime, we have a substrate containing some calcium-based minerals. There's calcium carbonate. In this case, as you know, we have a CSH, calcium silicate hydrate. So a mineral that is less soluble than calcium, so they can provide less calcium compared to calcium carbonate. But let's say to solve the issue, it's possible to add calcium ions directly into the PAP solution, okay? So it's possible to favor the reaction, the formation of calcium phosphates. So also in the case of cement, what we found was some improvement in mechanical properties, for instance, in terms of compressive strength, but then we tested also many others without any, let's say, significant color change. So also in the case of historical cement, it's possible to use the same technique to improve mechanical properties. Then we also investigated the possibility of using more or less the same technology in the case of new cement. In collaboration with a company, Saint-Gobain from France, that was interested in this technique, we first investigated, we screened different phosphate salts as precursors for the formation of hydroxyapatite. So as an alternative to DAP, the ammonium hydrogen phosphate, we considered potassium phosphate and sodium phosphate, because in this case, the advantage would be that we do not release ammonia in the atmosphere, which is good. So releasing less ammonia is good from the environmental point of view, and also in terms of smell, that the restorers, people that perform these treatments can smell. The, let's say, trade-off is that in this case, there are cations, sodium, potassium, that remain in the substrate, which in the case of stone is something that for sure you don't want. In the case of cement, because potassium and sodium are already present in the substrates, is something that maybe can be dealt with. So with some colleagues from Switzerland, we performed some thermodynamic modeling to predict what phases would form by using these 3 different precursors, and then we performed some experiments to check the formation of hydroxyapatite, and as you can see there, in all cases, hydroxyapatite was formed. Then we performed some performance tests in terms of resistance to abrasion, and ability to prevent staining. So in the end, as you can see, both DAP, the phosphate based on potassium and sodium, they all provided good results. In terms of anti-stainability, potassium and sodium provided even better results. So in the end, we selected the potassium phosphate as a good candidate for further tests. What we investigated was what concentration of this phosphate precursor to use in the end. So we compared different concentration, 0.1 molar, 1 molar, 2 molar, and intermediate concentration was found to be the best, because otherwise you form also some undesired phases like this one. And then we investigated at what time after the creation of cement is best to apply this treatment, like 1 week, 1 day, 3 days, 1 week, 28 days, and so on. And in the end, we found that the maximum effect is reached when you apply the phosphate treatment after at least 28 days. So you need to allow curing time for the cement, because if you apply the phosphate treatment like after 1 day or 3 days, then the phosphate treatment interferes with the hydration of the CSH. So there's some competition between these two processes, so it's best to apply it at a later stage. In a recent collaboration with some colleagues from, let's say, originally from China, we also try to clarify the mechanism that it's going on in the formation of calcium phosphate if you use DAP or the phosphate precursor. So in the end, the pH of the phosphate solution and also the presence of ammonium ions that can act as a buffer for the pH was found to be important parameters determining the formation of the new phases and also the decalcification of the CSH. So it's true that we want to form a calcium phosphate for the reasons that I explained, but when this calcium comes from the CSH especially, and calcium hydroxide or calcium carbonate, then it might become problematic, okay? You don't want to consume your CSH to form the calcium phosphate, because otherwise you strengthen your material, but you take out strands from the material itself. So it becomes counterproductive. Okay, last two topics that I wanted to present. So one is the possibility of using phosphate treatments to provide self-healing action. So self-healing, I don't know if you are familiar with that, if any of you is studying this. So usually it's obtained by using bacteria. What kind of bacteria? Bacteria that through their metabolism can form calcium carbonate. So here you can see a nice SEM image, scanning electron microscopy image of bacteria that produce the calcium carbonate, and in the end they were buried in their own calcium carbonate. This has been exploited because when you have ordinary concrete with no self-healing action, nothing strange, you have the concrete, you have the steel bar, you have problems when the concrete cracks, so that water, oxygen, and so on can reach the reinforcement bar, and so you have a corrosion starting. The idea of this self-healing concrete is to include in the concrete capsules containing the bacteria or spores of the bacteria. So when the concrete starts to crack, you have the capsules containing the bacteria that are cracked out, open, they release the bacteria. The bacteria form calcium carbonate and are able to close the crack before it reaches the bar. And so you are able to prevent or at least delay the corrosion of the steel bar. This has also been, let's say, demonstrated in several studies in different ways. Here, for instance, you can see a crack that is progressively closed after 3 weeks, thanks to the formation of new calcium carbonate crystals, which are formed by this bacteria. Here you see like some other details about this technique. So this is the, let's call it, traditional way of obtaining self-cleaning action. A different strategy is based on phosphate, on the phosphate technology that I presented. So the idea is to incorporate in the cement, in the concrete, some hydrogel containing a phosphate precursor. In the case, again, it's sodium phosphate. When a crack develops in the concrete, then the phosphate precursor is released from the hydrogel. It's able to react with calcium ions that are present in the pore solution, with the water that is present in the environment and comes in from the crack. And to, in this way, that's formation of a calcium phosphate and there's healing of the crack. So for instance, here you can see like the compressive strength of concrete when it contains the hydrogen with the phosphate precursor. After, I mean, there's a progressive increase in compressive strength when you induce cracking and release of the phosphate precursor. So in this study, it was demonstrated that it's possible to recover the mechanical properties of compressive strength thanks to the healing action of the new calcium phosphates that are formed through this mechanism. Okay, very last, let's say, topic is the possibility to exploit the phosphate treatments to obtain an anti-corrosion action. So here you see this weird thing here, which is called a hip implant. So the inspiration from this came from the biomedical field. As I mentioned at the beginning, there are several cases. Here is problems at the hip, where people need metallic implants made of usually titanium, which is usually or always covered with a thin layer of hydroxyapatite, because this hydroxyapatite is a bioactive material. It means that cells in our body recognize this hydroxyapatite, and in this case, also the titanium implant covered with hydroxyapatite, as something friendly to our body. So the cells and the new bone is able to grow over or through this hydroxyapatite layer. Whereas if you use the titanium alone, this is a bio-inert material. It means that it's not toxic to our body, but our body doesn't recognize it as something, let's say, friendly. So there's no formation of like a good adhesion between the metal and the bones. So there is some problem, some limitation. By forming this hydroxyapatite layer over titanium, it's possible to make the implant much more friendly, let's say, to the human body. How do you form these hydroxyapatite layers over titanium? Here is when the electrodeposition comes in. Of course, we are not going through all the reactions. The idea is to form hydroxyapatite over the titanium implant. You make it work as the cathode in a system. I don't know how familiar you are with the electrochemistry, but the idea is I place my implant in a bath containing a phosphate salt, the same DIP that we saw. I connect it to an anode and then I apply current. Through several reactions, by making this work at the cathode, it's possible to have formation of a thin layer of hydroxyapatite on the surface of the implant. So, why do people do so? First reason, to make the implant more friendly to the human body. Second reason is to decrease the corrosion of the metallic implant itself, because our body is like an aggressive environment. It's not like standing out in the rain, but still in terms of pH, in terms of presence of ions and so on, the so-called or body fluids, which in the lab are reproduced by using simulated body fluids. Again, they are an aggressive environment. So by forming hydroxyapatite layers on the surface of the metallic implant, it's possible to reduce its corrosion. Here in this graph, you can see a comparison between an untreated metallic implant and the same metallic implant with some coatings formed by electrodeposition on top. So there's a shift in this direction in this graph where you have the potential and the current. So it means that the less current circulating in the system, so decreasing corrosion. By taking inspiration from this, we performed some studies and we recently filed a patent at the national level and then international level. The idea is, again, to treat like a concrete pillar with steel bars. You apply phosphate ions from the exterior, and by a single treatment, you are able to improve both the cohesion of the cementitious layer, so you make it denser, more cohesive, you improve mechanical properties, and you can improve the corrosion resistance of the steel bars. So by a single treatment, you can obtain this double effect. Okay, conclusion. So I hope I showed you that and I convinced you that through this phosphate treatment, so applying a solution of DAP to form hydroxyapatite can be an effective strategy for conservation of stone and mortars, frescoes, and so on in a more effective way than commercial treatments, both in terms of technical performance and also in terms of environmental sustainability. Here, the solvent is water, which makes it a greener, a more sustainable treatment compared to the commercial alternatives. Starting from this, in the last few years, we in Bologna, but also other groups, let's say around the world, also in China, there are several groups that are working on that. It's possible to, let's say, transfer from the cultural heritage to the cementitious world, so cement, mortars, concrete, and so on, to achieve some interesting properties, including the self-cleaning ability and anti-corrosion ability. Okay, I would like to thank and acknowledge the contribution of many people that over the years I worked with, starting from my, let's say, former mentors and supervisors to students that I've been supervising myself. For the part of the study that was about the antimicrobial ability and so on, I would like to acknowledge these colleagues and the Italian government for the funding. And then I thank you all for your attention, and I'm open to any questions if you have any.